Okay, so this PVA, otherwise known as motion, we call it that because the three main concepts start with P, V, and A. So what do you think P stands for? Position. Now, position is most often represented by x of t. This is a particle moving along the x-axis, so that would be right and left. Sometimes we use y of t. This would be a particle moving along the y-axis, up and down. And sometimes when you're just talking about like a more general case, like a rocket or a car, sometimes we use s of t. But this is kind of like the main function, so I'm going to call that f. All right, what about v?
Velocity.
Velocity. And velocity is always just represented as v of t. Now, how is velocity related to position? It's the derivative. So I'm going to put a little f prime over here. Now, if we're talking about instantaneous velocity, which is usually implied if nothing is there, that's the derivative. There is such a thing as average velocity. We'll talk about that in a few minutes. So you can have a rock or I rock. All right, it's not always the derivative, but it is a lot of the time. And so the a then would stand for acceleration, the rate of change of the rate of change. And that would be f double prime. So if you notice, we have f prime, f double prime. This is pretty standard. This is what we just did a whole chapter on. So we're going to use a lot of those concepts that we learned last chapter. And I think giving a context to it is going to help you learn that stuff even better. So we got to get some of this phrasing down first, though. So if we have a particle that's moving left or right, then that's what x of t is implying there. Okay, so what would initially mean? Something equals 0. What do you guys think? I said initially, blah, blah, blah. That would be at the very beginning. I get why some people would say position, but it's actually time. If you want position to be 0, a better way to state that is at the origin. Because origin kind of has the connotation of a location, whereas initially, that implies time. Okay, what about at rest? Velocity. And this does not mean that this particle is at rest and it stays at rest. It could be the particle is moving right, stops for a split second, then moves left. In between those, the velocity would have to equal 0. Okay, what if the velocity of a particle is positive? This is what sets velocity apart from speed. Speed is just how fast something is going. Velocity is how fast something is going in the direction. So if a velocity of a particle is positive, then the particle is moving to the right. Now that's only in the case of this x of t. In the case of y of t, what direction would that be? Up, right? It would either be up or down, and up would be the positive direction. And then for s of t, this could maybe mean forward. Okay? It'd be the positive direction. So on the flip side, if the velocity of the particle is negative, then that particle is moving to the left or down or backwards. Okay, so I kind of already hinted at this, but we do have average velocity. This is like average rate of change, AROC. Okay, to find average velocity over a time interval, divide the change in position by the change in time. Okay, so notice that I'm not actually averaging anything. I'm just doing how far did the particle travel divided by how long did it take for that particle to travel. And that's average velocity. That's something you've already been doing in classes before this one. Instantaneous velocity, that's unique to calculus. This is IROC. I'm going to go ahead and write this. AROC for number 6, IROC for number 7. This is when the velocity is at a single moment in time. This is when you're doing derivative. Okay, what about if the acceleration of the particle is positive, or you're accelerating? Then what is increasing? I'm going to go ahead and use velocity. We're going to talk about speed tomorrow and how that's a little different than velocity. Today we're just going to stick with velocity. And this is pretty intuitive when you're going in the positive direction. If you think about it, you're in your car, you put your foot down on the gas, you accelerate, your velocity is increasing. But you can do those similar things going in the opposite direction, and then it becomes less intuitive. That's when we're going to rely more on what we already learned in last chapter. Okay, so what do you think should go in the next blank? If the acceleration of the particle is blank, then the velocity is decreasing. Negative. And in order for a particle to change direction, the what must change signs? Velocity. So velocity is positive, particle's moving to the right. Velocity is negative, particle moving to the left. When you get that change from positive to negative in velocity, that's when we have a change in direction. Okay, so here we have an example, and this would be position. I know it's position because it's x of t. Okay, so if I wanted to do velocity, and I'm not saying average or instantaneous, I'm just saying velocity. What's implied here is instantaneous. Okay, so we're going to take the derivative. Don't get caught up on these fractions. They're generally designed to make your life easier. So this would be velocity. And then likewise, acceleration, we'd take the derivative again, the second derivative. So 2t minus 2. And in a problem where you have all three of these, you can answer so many types of questions. When is this particle moving to the left? When is the speed increasing? When is the particle at rest? When does the particle change directions? All sorts of stuff, and it looks very much like chapter 3. Before we get more into that, I want to look at a table. Okay, because these problems are a little bit more conceptual. Some of you are going to like these more because you really don't have to do a whole lot of like work, but you do have to do some analyzing. Okay, so I want you to read through this and look at the table and kind of see if you can have a picture of what's going on with the particle. Okay, the biggest thing that I notice with students here is they look over this part. They don't really get that what they're given is velocity. This is like me giving you f prime. So sometimes I'm going to ask you to kind of go backwards. Sometimes they're going to be asked to go forwards. But either way, you have to really make sure you understand what you're given. Okay? So the velocity starts out negative. Then it goes positive, and it looks like it kind of increases at some point and then decreases. Okay? So if you have an idea of what's going on, that's definitely can only help you. It also says that the velocity is a differentiable function. What's implied here? Continuous. So you have a continuous differentiable function, and I see a closed interval happen later on in the problem. Does that make anybody think of something?
Oh, MVT?
Yeah, MVT, any theorem. This meets those conditions, so we can apply the theorems. Okay, so at t equals 0, is the particle moving to the right or to the left? So what do you guys think? So at t equals 0, I heard some rights, I heard some lefts. What is the velocity? It's negative. So that would imply left. Okay, and our reasoning is because v of 0 is -3. And I'm going to go ahead and put the units here since they give them to us. Meters per minute. You could say this in words. The velocity is negative. You would just have to say at t equals 0. I've implied all that right here. So if you're like, what's the least amount I can write? You can't write any less than this. Okay, what about, is there a time during the interval, 0 to 12, closed interval, when the particle is at rest? So what did we just say meant at rest? When what's 0? Velocity. When velocity is 0. So I don't see a 0 in the velocity row. Is it implied anywhere?
Yes.
Where?
Negative opposed.
0 to 2.
On the interval 0 to 2. There has to be a 0 in there. And the only reason there has to be a 0 is because this thing is continuous. This function is continuous. So we have to explain our answer. Now this whole is there a time, that means we're probably going to need to reference a theorem. You could explain what the whole theorem means, but by referencing the theorem, you're actually really saving yourself a lot of work. So we're going to go yes. Okay. We're going to list the conditions. If we're going to quote a theorem, I need to list the conditions. Now for the theorem that we're going to use, I haven't said it yet, we really only need to list continuous. That actually gives you kind of hint as to which theorem. Now, 0 is between -3 and 2. I'm going to list that out. -3, is less than 0, which is less than 2. I'm going to relate it back to the function. What was -3? It was v of 0. What was 2? It was v of 2. IVT. What was your, how did you know it was IVT and not something else?
Because we wrote these little things.
We wrote the inequalities, and the big word here is between. Okay, when you're saying, oh, 0 has to be between these two, that's intermediate value. Intermediate and betweenness, they're related. So by IVT, then we can say v of t equals 0 on what interval? Now you can go ahead and say 0 to 12, that's fine. But what did I really show right here? On which interval? 0 to 2. And if this happens on 0 to 2, then of course it's going to happen on 0 to 12. So the question I know is burning in your mind is, do we have to write all of that? And the answer is yes. But feel free to write much more. You need to show the work. Is there a time on an AP test where they still give you full credit if you don't quite write all of that? Sure. Is there time when they take off if you don't write continuous? Yep. And you're not going to know when. So I want you guys just to get into good habits and cover everything. Okay, so let's look at 3. 3 says use the data in the table to find an approximation for v prime of t. So automatically I'm writing v prime of 10 is approximately, that little squiggly equal sign. Now I can't find, first of all, I don't even have v prime. Second of all, I don't have a 10. I know that a 10 is going to go in between 8 and 12, but even if I had a 10 column, I couldn't just pick out that number because that would only be the velocity. It wouldn't be v prime. So what can approximate v prime? What can approximate the instantaneous rate of change? Yeah, so you're all kind of, I'm going to put everything y'all just said. We can approximate the IROC with the AROC. We can do v of 12 minus v of 8 over 12 minus 8. The average rate of change from 8 to 12 is the closest thing I'm going to get to the exact rate of change at 10. This does turn out to be 5 minus 7 over 12 minus 8. And if you wanted to simplify, although that would not be required, you'd get -1/2. There's a reason why you might want to simplify. There's multiple choice problems where that would be required. It could be that I want to use this number in the next part Okay, but it's not required. What is required, though, is that you show your work. If all you write down here is -1/2, you're not going to get the credit because it does specifically say, show the computation that lead to your answer. Okay, so let's talk about the indicating units of measure. So if you're not quite sure what they should be, think about, well, what was the units for 5 and 7? And 5 and 7 I got from this row. So I go over here and I say, oh, that's meters per minute. So I write that on top. And then what were the units for 12 and 8? So I follow that over there and I go, oh, that's minutes. And of course, you could write meters per minute squared. So I'm writing all of this down. You didn't have to simplify either the units or the number. I'm just writing it down so that you have it. Some of you said acceleration. So I'm going to use that in our explanation. Because it said explain the meaning of this. Okay, this is going to be the particle's acceleration at a specific time. At what time? At 10. Sorry, this would be S for seconds. Is about -1/2 meters per minute squared. You could have said the particle's average acceleration is -1/2 meters per minute squared. That would have been fine. So it's all the same stuff we'd already been doing, now in a new context. Okay, number 4, let A of t denote the acceleration of the particle at time t. Is there guaranteed to be a time? There should, at this point, start to be a little ringer going off in your mind going, this is probably a theorem, and the answer is probably yes. It doesn't have to be, but it tends to be because those are more interesting problems. Okay, so is there a time, is there guaranteed to be a time, such that A of c equals 0? All right, so let's look back up here. In order for the acceleration to be 0, what would need to happen with velocity? Well, let me ask you this. Can I say that again? So what would have to be 0? The acceleration. So what would that mean for velocity? If velocity would have to be constant or be a number and then come back and be that number again. Okay? So like if you were on the highway and you were driving 60 miles an hour, okay? And then you decided you wanted to speed up to pass someone, and then you returned back to 60 miles an hour. And all that was recorded was the 60 miles an hour and the 2 times. What would your average acceleration be? 0. Your velocity would be 60 at both times, but your average acceleration would be 0. So what I want to do is kind of point out what's happening here. And next time you're going to know to look for this. When you see a velocity at a number, and it doesn't even matter what happens in between. Does not matter. That 7 makes no difference. And then it returns to 5. I get that it wasn't 5 the whole time. It didn't stay 5. It changed. But the average acceleration from 6 to 12 is 0. What theorem tells me that the average acceleration being 0 implies that the instantaneous acceleration is 0?
MVT.
That's MVT. Okay, so let's write out our answer here. Let's go ahead and say yes. Okay, and let's go ahead and write our conditions. And let's show that we know that average acceleration is 0. And it was from 6 to 12. Okay, so that would be v of 12 minus v of 6 over 12 minus 6. Now I'm trying to prove this equals 0. So if it doesn't equal 0, then I have an issue. I need to go back and figure out where I made a mistake. Now because v of 12 is 5 and v of 6 is 5, this works out perfectly. The average acceleration is 0. So you don't have to go through and explain that whole thing about the average acceleration equaling the instantaneous acceleration. That's by quoting MVT, you've done that. This is why it's good to know the names of the theorems. By MVT, now we just have to list out what it tells us. A of t equals 0. And I do need to list out on what interval. Now, I could go ahead and write 0 to 12. Okay, but what interval did I really prove this happened? 6 to 12. That's a better answer. I will tell you, you would get away if you wrote 0 to 12, and I wouldn't take off for that. 6 to 12 though is a better answer. Okay.
So it doesn't have to be just like a 0 over 0. It can be 0 over number.
Right. If it was, and it won't be 0 over 0.
Yeah.
Because if it was, that would be a problem.
Yeah.
Yeah, so what you're really looking for, though, is just that velocity is a number and it comes back to being that number. Okay, let's look at the next page. So that was a table that used some of the theorems. Some of you are going to like that kind of problem the best. Others of you are going to really like the graph problems better, okay? So if you just hated that last one, you might like this one. Again, the big thing here is you've got to recognize what they're giving you. Okay, this is not a picture of a particle going up a mountain, coming back down a mountain, splashing into the ocean, and then staying sunk. That's not what this is a picture of. It's not a slide. Okay, what this is the velocity. So I want you to write that really big somewhere on your paper so that you don't forget this is velocity. Okay, the velocity starts off positive, which means which direction does the particle start out traveling? To the right. And what's happening, if you kind of follow my little pin here, what's happening to the velocity? It's increasing. So the particle is still moving to the right and it's speeding up. What happens right here? The velocity is decreasing. But what direction is the particle still traveling? Still traveling to the right because the velocity is still positive. And then at 5, what happens to the particle? Changes direction and starts moving to the left. It speeds up, and then it levels off at a certain speed. Again, we're going to talk more about speed tomorrow. I'm just kind of using that to give you a framework for the problem. So when you're asked questions about this, if you're not looking at this graph as velocity, you're going to get every single problem wrong, which is not good, obviously. So at t equals 4 seconds, that would be right here. Is the particle moving to the right or to the left? So we kind of just went over this, but what do you think? To the right. To the right, and then we got to explain it. Because v of 4, now you can actually list out what it is. The important part here is that you say something about greater than 0 or is positive. You don't have to write out what v of 4 actually equals, although that would be fine. So if you want to know what's the least amount I can get away with, it's this. Over what time interval? So here my answer is going to be like parentheses and commas and stuff. Is the particle moving to the left? So we just got through saying that everywhere above the x-axis, the particle moves to the right. So what's the answer to 2? 5 to 9. Notice I'm using parentheses. It would be easily forgiven if you wrote brackets, both by me and the AP graders, but most teachers and college professors would prefer you to write parentheses here, because at 5, the particle is actually not moving at all. So 5 to 9, we still got to write a because statement, an explanation, and that is because v of t is less than 0. And of course you could say is negative. You could write out the word, the velocity is negative. There are multiple ways to express that thought. Okay, so notice the graph was velocity and we were asked about velocity. So I just looked at the x and y values. I hadn't yet even really looked at the slope yet. That's what number 3 gets into. So at number 3, it starts asking you about the acceleration being positive or negative. This is when you're going to look at the slope. Okay? So at t equals 4, because velocity is decreasing, or you could say the slope, or v prime, is negative, then we know that that acceleration is negative. The easiest way to explain this is to say v of t is decreasing. And I'm going to go ahead and put in at t equals 4. Because if you notice, on each thing I refer back to the time, and that's important in your explanation. It's not decreasing everywhere. V of t is only decreasing at t equals 4. You want to refer in each problem, each answer, to the time. Okay, average acceleration. We have not yet done this exactly, use this phrase, but we kind of did it in the last problem. It's not asking you to find acceleration and take an average of values. It's really just asking you to do that whole v of something minus v of something else over subtracting those two, just like how we did. So what numbers do you use? You use the numbers they tell you to use, 2 and 4. Convention puts the bigger number first. As long as you stay consistent, it would be okay for you to write v of 2 minus v of 4 over 2 minus 4. You just can't, you just got to be consistent. Okay, so here we're going to actually have to look at values. So v of 4, we have to actually look up, okay, what is that y value? And that's going to be easier for you to do on your paper than looking up here. So what do you think? What's v of 4? 6. We're just looking at the y value. What about v of 2? 9. And again, it would be okay to leave it unsimplified. If you did simplify it, and there's a good reason why you might want to here, you would get negative 3/2 feet per second squared. It helps us with number 5. All right, it would be okay to leave it unsimplified, but if all you wrote down was negative 3/2 because you just did like rise over run, you wouldn't get all the credit because it specifically wants you to show the computations. So you just, you know, that's not my rule, that's just something we have to do. Okay, so let's look at number 5. It says, is there guaranteed to be a time? I see that phrase again. Is there guaranteed to be a time? So what are you thinking? Some theorem. So the next thing should either be talking about in between values, which is like intermediate value theorem, extreme values, like absolute max or min, or it should be talking about something about the average rate of change equaling the instantaneous rate of change. Now, for this exact problem, I'm kind of already going into this a little overkill because we just already found this. Like, y'all see how the interval is the same, negative 3/2 is the same, and v prime of t would be the slope. So you could actually get away with explaining this in less words. Are the conditions, so which theorem is this leading us to? MVT. Why do you say that?
Because
we just did the average rate of change, and this is asking us about instantaneous rate of change. So the conditions for MVT are that this graph, v of t, should be continuous and differentiable. Is this actually differentiable up here? No. So that's kind of an issue, which makes this not really the best problem to ask. Okay, but I kind of want to stick with the theorem because I think we just need to practice it. Okay, so we're going to say yes, by mean value theorem, v prime of t equals negative 3/2 feet per second squared. This problem could have worked out slightly different, and I think about this, I've kind of cut and paste this from other things, like literally cut and paste them on paper with Scotch tape. And my goal is to retype this at some point, and I kind of want to change this just a little bit. But okay, let's not think any harder than that about that one. Not the best problem. And let's look at number 6, and this is one I want you to try to do on your own. It actually refers back to the previous page, but I want you to read 6 and see if you can answer it, and go ahead and put down your best guess. Okay, so the answer is either 3 or 5. So we want to know, when did this particle furthest to the right? Okay, we're doing number 6. I'm just doing this here. So let's start over at the beginning. This particle starts off already going, and it starts getting faster and faster, and it's moving to the right, correct? So it's moving to the right. And what happens up here at 3? Does it change direction? It keeps moving to the right, but it slows down. So at 3, it's still moving to the right until 5. And at 5, that's when it turns around and starts going to the left. So that's why the answer is 5. This type of thing, we're not going to explain it. That's typically multiple choice. Okay, last example we're going to go through. This is the one that really, if you did well last chapter, all of this is the same stuff. If you didn't do well last chapter, I think me giving this context would help you get better at that stuff. So particle moves along the x-axis. I know it seems like they're all x-axis. Occasionally they throw a y-axis one in there, but most of them are x. And you got to know, what are they giving you? Are they giving you position, velocity, or acceleration? Position. That's important. You have to know which one they're giving you. At t equals 0, is the particle moving to the right or to the left? This implies direction. That means we need to find velocity. So when you're given an equation, this is kind of how we started off the lesson. You just take derivative. 3t squared minus 12t plus 9. Please be careful here. If you make one tiny arithmetic error, all your answers are going to be wrong, and they're probably going to be harder for you. So just be really careful with that. And we want to know, okay, well, what is the velocity at 0? So you don't need a calculator here to plug 0 in. Some of these are going to be calculator problems, but this one's really not that hard to do without. So what is v of 0? 9. The big important thing is that this is positive, right? So which direction? To the right, because v of 0 is positive. Okay, 2 asks about, is the velocity increasing or decreasing? So what do we need to do here? Find the acceleration. Find the derivative of velocity. So what would that be? I know I can, right about this time in each class, it's like I'm just losing y'all. So I'm going to speed this up here. So we want to know at 1. So 6 times 1 minus 12. That's negative 6. So negative, that implies, decreasing. So decreasing because, and now here you could write a of 1. You could write v prime of 1 is negative. You could say is negative. You could say less than 0. That's where you have a little bit of choice here how you want to do it. Okay, and this 3 is going to be where we end. I know your paper has some stuff after it, but we'll stop here after we do 3. So now I'm not analyzing a specific value. I'm trying to find the values for which the particle is moving to the left. So left means I want the velocity to be negative. So we already found the velocity, right? So basically I want to know where is 3t squared minus 12t plus 9. Where is that thing negative? Okay, and just like how we did last chapter, the first thing I need to do is figure out where is that thing equal to 0. And then do a sign chart. So how would we solve this with a calculator? Solve feature would be the easiest way to do it. Without a calculator, we would need a factor. Sometimes these are with, sometimes they're without. I'm going through this part quickly. Just factoring. Does this 3 out here give me a solution? No. That was something some people missed on the test. So I end up getting t equals 1 and t equals 3. These are like critical numbers, basically. Okay? So what I'm going to do is put them on a sign chart. By the way, if one of these numbers had been negative, I would totally disregard it. Because with time, we are going to start with 0. We're not going to look into negative time. That's a thing, but not for us. Okay, so down here, we're going to test this in velocity, and then that's going to tell us something about position. So we already know what happens when we plug 0 into velocity. That's what we did up here in part 1. We found that velocity is positive. Now, normally I would write like an increasing arrow here, but I want to be real specific. I'm just going to write a big R for right. If velocity is positive, the position or the particle is moving to the right. Now, none of these were double roots. None of these were double solutions. So we know it's going to work out really nice where it just flip-flops. If you didn't know that, you could test it. So what are the values of t for which this particle is moving to the left? 1 to 3. And our justification is because v of t is negative.